Hello all, welcome back to Introduction to Atmospheric Dynamics. We're continuing our discussion in Chapter 3 on the applications of the basic equations. In this section, we're turning our attention away from natural coordinates and turning our attention towards another related concept that emerges naturally from the scale analysis of the equations of motion that we derived in Chapter 2. In this section, we're focusing on the thermal wind, which provides a natural mechanism to relate temperature and wind speed. The fundamental question underlying this lecture is there a relationship between wind speed and temperature? And it turns out that actually there's a very simple relationship that emerges from geostrophic balance. It turns out that there is actually a close link between vertical wind shear, which is the vertical gradient of the horizontal wind speed, and layer thickness. Recall that layer thickness, which represents the distance between subsequent pressure layers, is governed by the volume of the fluid, which is determined by the temperature of the fluid. Warmer air parcels tend to be thicker than cooler air parcels, and consequently the geopotential height field tends to be pushed up for warmer regions. Let's look at this diagram of 300 hectopascal wind speed, which describes an upper level region in the troposphere where we would expect to see high wind speeds associated with jet-like features. So the question becomes, where are the strongest temperature gradients at levels below the 300 hectopascal level? In this diagram, you'll notice that we have strongest wind speeds associated with regions where we have geopotential height contours that are bunched very closely together. This gives some indication about where the temperature gradients are going to be strongest in the lower regions. In fact, if we look at 850 hectopascal temperature, which represents temperature at a lower level, what we see is that the strongest change in temperature is actually occurring in regions that are effectively coincident with where the wind speeds at the upper level are the highest. So here we see that the temperatures change most rapidly when they transition from green to blue here. If we look back at the wind speed diagram, these are the regions where we have the warmest colors and the strongest wind speeds. This relationship actually pops out fairly naturally from a very simple analysis that we'll then assess within this section. So by definition, the thermal wind is a vector difference between the geostrophic wind at an upper level and a lower level. So keep this in mind. It is not a real wind, but it's instead a vector difference of wind speeds at upper and lower level. What we notice when we have tilting geopotential surfaces, such as shown in this diagram, is that when you have very sharp tilt, this is associated with a strong geopotential gradient, and consequently, through the concept of geostrophic balance, these highly tilted surfaces are going to be associated with the strongest wind speeds. On the bottom, where we have only a lightly tilted surface, we have a much weaker geostrophic wind speed. So what you'll notice from this diagram is that on the left-hand side, where we have cold air, the distance between geopotential surfaces is much smaller. This is because the air is cooler and hence occupies less volume. In the warm regions, what we have is that the layer thickness is much larger. That is, the warm fluid takes up larger volume and consequently pushes up the geopotential height surfaces. Because of the fact that this accumulates with altitude, what we see is that the increased volume required in the warm region leads to a much stronger tilt at upper levels. So whenever we have this horizontal temperature gradient, that is, a temperature gradient between a cold region and a warm region, it induces a tilt on the geopotential height surface above it, and consequently through the geostrophic wind relationship then induces a change in the geostrophic wind. So the emphasis again here is that this thermal wind concept is not a real wind but is a vector difference. The thermal wind vector itself is then defined in such a manner that cold air is always to the left of it and warm air is to the right. It tends to flow parallel to isotherms, that is, lines of constant layer temperature. Cold air is to the right and warm air is to the left in the southern hemisphere. Okay, let's derive this then quantitatively. So the geostrophic wind is the component of the real wind that is governed by geostrophic balance. The equations on the right-hand side here show what that geostrophic wind relationship looks like on height surfaces. In pressure coordinates, the relationship takes on an analogous form, or a much simpler form, which looks like basically the zonal wind being related to -1/f times the meridional derivative of the geopotential height field, and the meridional wind being related to 1/f times the zonal derivative of the geopotential height field. So let's take these two equations as our starting point. We're going to differentiate these with respect to P. Recall that P is our vertical coordinate in a pressure coordinate system. So by differentiating with respect to P, we're trying to understand how the geostrophic wind changes with altitude. This gives us two equations. On the left-hand side, we have that the change in the zonal geostrophic wind is then related to both the y derivative and the p derivative, the second derivative, that is, in y and p of the geopotential height field, whereas the meridional geostrophic wind is related to the zonal derivative and the p derivative of the geopotential height field. We can then apply the hydrostatic relationship in pressure coordinates, which allows us to then write the derivative of the geopotential height field with respect to p as simply -RT/P. This holds on constant pressure surfaces. Then, applying this to our second line of equations, we end up with what is known as the thermal wind relationship, which is a relationship between the vertical wind shear, that is how the geostrophic wind changes with altitude, and horizontal temperature gradients. You'll notice that these two are directly proportional to one another up to a constant given by R/PF. So as mentioned, this relationship then allows us to link the horizontal temperature gradient terms with the vertical wind gradient, or vertical shear. Note that since this calculation is performed on constant pressure surfaces, the term R/PF is actually constant on these pressure surfaces. Okay, now recall that the thermal wind relationship here does not describe the actual thermal wind, which is a vector difference. Instead, this describes vertical shear of the geostrophic wind field. In order to actually obtain an expression for the thermal wind, we need to integrate these equations vertically so that we can obtain a difference with altitude. Okay, so let's do that. In order to begin, what we're going to do is multiply these equations through by p and use the fact that the derivative with respect to log p is equivalent to p times the derivative with respect to p. That allows us to incorporate the log p into the bottom of the derivative operator. These equations can then be integrated with respect to log p in order to obtain an expression that represents a difference between two pressure surfaces. Here we're going to define P2 as the pressure surface at the upper level and P1 as the pressure surface at the lower level. Note then that P2 must be less than P1. The thermal wind, which is then this vector difference, emerges from the fundamental theorem of calculus and takes the form shown here. For the zonal component of the thermal wind, we obtain an expression of -R/F times the derivative of the mean layer temperature in the meridional direction times the logarithm of P1 divided by P2. Note that this logarithm is then taken of a quantity which is greater than 1 and is hence a positive value. The meridional component of the thermal wind appears in an analogous expression except with R/F times the derivative of the mean layer temperature in the zonal direction times the logarithm of P1/P2. Okay, so these two expressions then, given a mean layer temperature, a latitude, and two pressure surfaces, allows us to compute the thermal wind. The thermal wind can also be computed from simple vector relationship by looking at the difference between the geostrophic wind vectors at the upper level minus the geostrophic wind vector at the lower level. In the bottom diagram, we see that the upper vector represents the geostrophic wind speed at 500 hectopascal, and the bottom vector represents that at 1000 hectopascal, that is, near the surface. The thermal wind within this region is then the red vector, which is obtained simply by Ug at P2 minus Ug at P1. Note that an alternate form of the thermal wind can also be obtained in terms of geopotential by using the hypsometric equation in order to rewrite the expression from the previous slide. Here we have that the thermal wind vector, which takes the form Rd over F times K cross the gradient on pressure surfaces of the layer mean temperature times log P1 over P2, can be rewritten as 1 over F K cross the gradient on pressure surfaces of geopotential at an upper level minus geopotential at a lower level. This effectively just emerges because the hypsometric equation allows us to directly relate the layer average temperature to the thickness of that layer. In component form, we obtain the expression then shown here in the blue box below. Note that the index 1 indicates the lower level and index 2 indicates the upper level. Okay, so from the thermal wind that we obtained earlier, we can obtain some rather interesting results. So first of all, note that the thermal wind always points parallel to lines of constant layer temperature. This can be proven by dotting the thermal wind with the gradient of the layer mean temperature. Recall that the gradient always points in the direction of steepest increase of the layer mean temperature, and hence it is perpendicular to lines of constant layer mean temperature. So if we find that this dot product is equal to 0, that means that the two vectors must be perpendicular to one another. And in fact, we obtain that that is the case through some pretty direct application of calculus. In fact, here we observe that the terms in the square brackets cancel each other directly, and so we get that this expression must be equal to 0. Okay, there's two concepts that then fall out from the thermal wind. We define a term known as veering winds as clockwise rotation of the geostrophic wind with respect to height. Here on the right-hand side, we have a lower level geostrophic wind shown with the purple vector and an upper level geostrophic wind shown with the blue vector. These vectors show clockwise rotation with altitude. That is, as you go up in altitude, as you go towards lower pressures, we have that the vector rotates to the right. The thermal wind vector, which is then the vector difference between the upper level geostrophic wind and the lower level geostrophic wind, is then shown here with the black arrow. It points along lines of constant temperature. Since warm air is always to the right of the thermal wind and cold air is always to the left of the thermal wind, then whenever this pattern emerges, it is indicative of the geostrophic wind advecting warm air into a region. Backing winds, on the other hand, are defined by counterclockwise rotation of the geostrophic wind with height. So at the lower level here, we have the purple vector, and the upper level we have the blue vector again in the lowermost figure. Here, with respect to altitude, we see a counterclockwise rotation as the purple vector transitions into the blue vector. The thermal wind vector shows up in black here, again pointing along lines of constant layer average temperature. Here, this particular configuration then gives rise to geopotential wind vectors which are indicative of advection of cold air. That is, they are pushing cold air into the warm region. We can also use thermal wind in order to understand the relationship between meridional temperature gradients and zonal wind. Here we have a meridional pressure cross-section of December, January, February, or Northern Hemisphere wintertime temperatures. Here you'll notice that the temperature is maximal near the equator, equatorial surface, and then tends to reduce as you go towards the poles. As you go up in altitude at the equator, you end up with lower temperatures near the tropopause, and then an increase in temperatures as you go up through the stratosphere caused by warming from the ozone layer. The wintertime pole tends to be very cold, whereas the summertime pole tends to be reasonably warm, and this defines the temperature contrast throughout much of the stratospheric region. Note here that the latitude is shown from 90 degrees south on the right-hand side of this diagram to 90 degrees north on the left-hand side of the diagram. The small white box in the bottom right-hand corner indicates the position of Antarctica. So in order to understand how zonal wind speeds behave in this cross-section, we're actually interested in examining the meridional derivative of the temperature field. The white lines that are drawn in this finger are indicative of a couple regions where we can sample the meridional temperature gradient. So I leave it to you to take a few moments in order to calculate the meridional temperature gradient in these regions, noting that the y coordinate increases from right to left. So hopefully your calculation corresponds to the signs that I depict on this figure. So in particular, on the lower left white line, we see a negative dy-t dy, that is, the temperature decreases as you go from equator to pole. At the tropopause level, we actually have a colder equatorial tropopause than a mid-latitudinal tropopause, and so this is associated with a positive dy-t dy. As we go to upper levels through the stratosphere, what we have is a fairly consistent negative dy-t dy. If we look now at the southern hemisphere, what we have is that as you go from South Pole to equator, we have a positive dy-t dy. However, at upper levels, the sign flips, and instead we generally see as you go from south to north that the temperature decreases. So using the thermal wind relationship, that allows us to actually obtain an expression for diug dy-p, which is the change of the zonal geostrophic wind with respect to the vertical pressure coordinate. So these two terms, diug dy-p and dy-t dy, are directly related to one another, and hence will have the same sign up to the F term, which also appears in this expression. So in the northern hemisphere, we'll observe that diug dy-p and dy-t dy have the same sign as one another, whereas in the southern hemisphere, where F is negative, the sign will flip. And so what we observe then is that in the lower left, we have diug dy-p is negative. Above that, we have diug dy-p is positive, and then negative through the remainder of the stratospheric region in the northern hemisphere. In the southern hemisphere, on the other hand, we have diug dy-p is negative near the surface, and then positive above the tropopause. We can then flip this around and use the fact that diug dy-z is proportional to negative diug dy-p because pressure decreases with altitude. This implies that as pressure goes to lower values, we must have that the altitude increases. So this is a direct sign flip from the diug dy-p values that we obtained on the previous slide. So in the northern hemisphere then, diug dy-z is proportional to negative dy-t dy, and you can see that here from the sign flip that emerges. In the southern hemisphere, on the other hand, we have that diug dy-z has the same sign as dy-t dy. So this is now useful because this allows us to figure out with altitude how ug is changing. Since we know that the geostrophic zonal wind is approximately 0 near the surface, that means that in the northern hemisphere we must have that the zonal geostrophic wind increases through the lower levels of the troposphere, and then as it hits the tropopause it decreases, and then in the stratosphere it increases again. In the southern hemisphere the picture is even clearer. We have that the geostrophic wind speed increases with altitude until it hits approximately the level of the tropopause, and then decreases through the remainder of the diagram, so through the remainder of the stratosphere. Let's check if this agrees with the plot for the meridional cross-section of the zonal wind. As you can see here, we obtain a direct correspondence with the approximate qualitative description we had on the previous slide. In fact, along the two black lines along the bottom, we have an increase in zonal wind speeds with altitude. So you'll notice that the plot goes from cooler colors near the surface to warmer colors in this region. This is where we find the tropospheric jets. or the mid-latitudinal jets associated with the atmosphere. Then, throughout the stratosphere, we obtain a difference depending on which hemisphere you're in. In the southern hemisphere, we have a decrease in UG with respect to altitude, which then leads to negative values of UG through the stratosphere. Or in other words, this corresponds to motion towards the west or an easterly flow. On the northern hemisphere, on the other hand, above the level of the tropospheric jet, we obtain that the zonal wind speeds increase with altitude, and so we see a move towards warmer colors and more westerly flow through the northern hemisphere. In order to identify the location of jets, we can look back at our plot of diUG, diZ and look for regions where we have an increase in zonal wind speed at a lower level and a decrease in zonal wind speed at an upper level. The region between those two white lines then suggests the presence of a westerly jet. As you can see between this plot and the plot on the following slide, these two regions show direct correspondence to the location of the jet.